Hi there. We just finished chapter 1, and that was kind of all things like points and lines, segments, angles, planes, all this very concrete, visual kind of stuff. Now we do this kind of start into the second part of geometry where we talk about reasoning and proof, and so we'll do a lot with theorems and definitions and stuff. So to start with, we're going to do 2.1 and 2.2 together here because they're both pretty quick assignment or quick lessons. 2.1 is on patterns and inductive reasoning. I'm going to skip this first activity. We did it in class, but inductive reasoning is something where you're using a pattern to make conclusions. And in math, we really don't do. We like what we call deductive reasoning, where there's proof of something that's very concrete. Inductive, if you're just basing it off a pattern, well, then it's got to be a pretty solid pattern for us to make conjectures from that. In this example, it says, look for a pattern. What are the next two terms in each sequence? Sometimes we're just talking about like a numerical pattern. If you can look at that and say it's 3, 9, 27, 81, well, I think we're just taking everything times 3, times 3, times 3. So we would just take our 81 times 3, and then that answer times 3. It says, what are the next two terms? Okay, I'm digging out my calculator here, stalling a little bit. Okay, so I'm going to take my 81 times 3. That's a 243. Take that times 3. I get 729. So the next two numbers would be 243 and 729. Sometimes we're looking for a pattern in a geometric figure. So in this one, if you'll take a look, it looks like we've got this circle. And in the first one, if you'll notice, it has 3 sides to it. The second one, the polygon, has 4 sides and then 5 sides. So I'm going to deduct then the next figure is going to be a circle, and it's going to have 6 sides. It's going to look something like that. And then I'm going to guess that the next one would be a circle, and it's going to have 7 sides. Now, a 7-sided figure is kind of tricky to draw. I apologize right now. I'm probably not going to get it right. 1, 2, 3, 4, 5, 6, 7. I did it bad. Undo. Let's try again. I think that first mark was probably too long, so I'm going to go 1, 2, 3, 4, 5, 6, 7. That's kind of bad too, but I'm going to blame it on the stylus. Okay. Now, I use this word conjecture, but let's talk about when I say that, if you're not familiar with that word, that's just a conclusion that you reach by using some of your inductive reasoning. So a conjecture is just some sort of thought that you maybe have that you can gain from looking at this pattern. Sometimes you're right and your conjecture turns out true, but sometimes you goof up and your conjecture ends up being false. Let's look at this next one. It says, what conjecture can you make about the 21st term in this sequence? The sequence goes RWB, RWB, and so I'm assuming it just continues in patterns like that, RWB, RWB. Well, since those are in sets of 3, RWB, RWB, and I'm looking at the 21st term, well, if I kept going with this, they'd be in 3s. 21 is a multiple of 3. It's going to end up being the last one in a set of 3. So I think that my conjecture would be it's going to be B. You try this one. What conjecture can you make about the 14th term? See if you can come up with what that one would be. All right, 14 is not a multiple of 3, so it's not going to end up being that last one like on this previous example. The 15th term would be, that'd be a multiple of 3, so the 15th term would end up being a B, so the 14th is right before it. It would end up being a W. Those are my conjectures. So let's make it a little fancier. What conjecture can you make about the sum of the first 30 even numbers? Whew, okay, 30 even numbers. So they've got it started for us. They've written out how many terms there are going to be. So just one term, the first even number is a 2. Okay, now if I take 2 even numbers, that'd be 2 and 4, and I'm adding those. 3, that's 2, 4, and 6. I'm adding them. And what I'm doing here is I'm looking for some sort of a pattern on these sums right here. Now, what this says here. Ultimately, what I'd like to be able to do, though, is look down the road, like to the, well, it says the first 30 even numbers, right? So I don't really want to continue this table for 30 steps. So I really need to, rather than looking at what's going on here and here and here, because I don't want to have to do, or I guess maybe what I should say is, I don't want to look at what happens from here to here, from here to here, from here to here. I don't want to do that. Because to get to the 30 even numbers, I'm going to have to do that list all the way to the bottom, all 30 rows. So I'd rather look at, well, what is this number? How does this number end up over there? Okay, so what could we do with this 1, 2, 3, 4 to get me my 2, 6, 12, 20? What do you think? All right. Well, maybe it's easier to start with the 4. And I think, what do I do to get that times 20? Well, that'd be a 4 times 5 would get me the 20. So if you look at the previous one, then it'd be a 3. And it'd be a 3 times a 4 gets me my 12. Okay. And then a 2 times a 3 equals 6. Okay, I think I see a pattern here. Because I'm going to take my number of terms here, and I'm going to multiply it by a number 1 higher than that. So 4 times 5. Oops, I missed my O. That's 20. Or 3, take times the number higher than that. That'd be a 12. All right, so what do you think? On the 5, if I had 5 even numbers I was going to add up, then I feel like that would be a 5 times 6, and it would add up to 30 then. Which kind of makes sense, because if you look at this, the next one would just be a plus 10, which would take me up to a 30. I like it. Let's keep going. Then this one would be a 6 times a 7. So if I was adding 6 even numbers, it would add up to 42. And then that takes us back to this part. What was the ultimate question was the first 30 even numbers. Well, then that would be 30 times 31, which is 930. Would be the sum of the first 30 even numbers. All right, this one's yours. There's going to be some like this on your homework, so I want you to kind of practice. Same question, but this is the sum of the first 30 odd numbers. So what you have to do is you have to start a table and kind of get it going and look for a pattern. Again, you want to look at the pattern of the, if this is how many number of terms, number of terms. And so you'd say 1, 2, 3, 4. And then if you need to have a column where you are adding these up, so one odd number is just 1. So then this is my total over here. 1. But if I had 2 odd numbers, that'd be 1 plus 3. 3 odd numbers would be 1 plus 3 plus 5. You finish out the total and come up with a pattern and see if you can answer the question on what's the sum of the first 30 odd numbers. Go ahead and take a minute to pause the video. Okay, this one ends up being a little bit easier, I think, and maybe it jumps out at you a little bit more. Remember that I'm not looking for a pattern this direction. I don't want to do that because I'm trying to get to the 30th one, and I don't want to make this table forever. I'm trying to get from how many terms there are straight over here to what this number is. Well, look at that. 4 gets me 16. 3 gets me 9. 2. Well, I'm just taking it times itself, or I'm squaring it, however you want to think of it, to get, if there's 4 terms, then it'd be 4 times 4. And that's where I'm getting the 16. 3 terms is 3 times 3. All right, so if I were to continue it, I'm going to guess that if there were 5 terms, they'd add up to 25. And 6 terms would add up to 36. But more importantly, 30 terms, that's what my question is. If I had 30 terms, well, that would just be 30 times 30, and that's 900. And that would be the sum of the first 30 odd numbers. We use these graphs sometimes to do these predictions and to look at what's going to happen. Here's a nice example. It's called a scatter plot with some points plotted in there. This is how many backpacks this particular company sold in the particular months of the year. It says, what conjecture can you make about the backpacks sold in June? Well, Here's the problem with sometimes making these conjectures. If this is May, then this one right here is June. And then you would just continue on down, and if you just followed kind of the path of it, I think it'd be about, well, if you look at your graph, be careful, because that actually lands at 0. And it's not like they sold 0, so you have to be careful on graphs. If they have that little break in there, like that one does, you can see that there's a pattern. It's going up by 500s, but it didn't want to start clear down at 0, and so they put a break in the graph. Now, if I hadn't put a break in it, then this right here would have been 7,500, and that would have been my estimate on that. That's 7,500. Now, if you kept going with it, it says, is it reasonable to use this graph to make a conjecture about sales in August? Well, that's June and July and August, and by then my line's way down here, and I know that that would not be a very good way to estimate it, because I know because of the break it's way off, it's off my graph. I'm just going to say, is it reasonable? No, it's off the graph. Now when you're making some sort of a conjecture, all of mine, I'm going to assume were right, and I think they were okay, but if I wanted to show that a conjecture was false, you just have to come up with one counterexample that says, that's not going to work, because here's an example where it didn't work. And so all you need is one counterexample. So let's look at some and see if we can come up with the counterexample. If the name of a month starts with the letter J, it's a summer month. Okay, so that's June, that's July, but there's one other counterexample I could come up with. My counterexample on that would be January. That is not a summer month. So if you can come up with one, you would say that that conjecture is false. B, you cannot connect any 3 points to form a triangle. I'm sorry, you can connect any 3 points to form a triangle. So that means, like, if I have 3 points, I could make a triangle out of them. Well, that would be proving it true. I'm trying to come up with an example where I'd have 3 points and I couldn't make that happen. Well, this is where it ties in from last chapter. What if your 3 points ended up being collinear? There's no way to make that into a triangle then. So this would be my counterexample for that one. This I wouldn't be using. When you multiply a number by 2, the product is greater than the original number. Well, you'd think multiplying by 2 would make it larger, but you always have to kind of think of the weird types of numbers. So I'm going to think of, what about negative numbers? If I take -1 and think about how big -1 is, and I multiply it by 2, now my answer is -2. How does -2 compare to the -1 I started with? It's actually a smaller number if you think it's farther left on the number line. So my -1 would be a counterexample for that conjecture. All right, so that was kind of just some little intro into some inductive reasoning. Let's talk about some conditional statements which tie in those counterexamples. It says here, well, a conditional statement, I like to think of it's like an if-then statement. If something, something, then something else. So if is like, if this holds true, then this is going to be my conjecture. This is what's going to happen every time. And you have to be careful with if-then statements because they're used interchangeably a lot, and they don't always mean the same thing. I thought this was kind of a cool thing, this bumper sticker. It says, if you can read this, then you are too close, which is kind of this classic hint, get off my tailgate, or get off my tail. And so if you see that, now that's a nice conditional statement. It's an if-then statement. If you switch it around, does it mean the same thing? Or could you find a counterexample or something? So it says, suppose this first one is true. So we're saying this is true. If you can read it, then you're too close. Are these other ones true or false? If it's true, that's great. If it's false, we should be able to come up with a counterexample. So it says, if you are too close, so we're switching it around here, if you're too close, then you can read this. Well, if you're too close, then you can read this. Can you imagine a scenario where you're too close to it, but you can't read it? Okay, there'd be a lot of ways. Maybe you're blind. You're really close, but you can't read it. Or maybe you're a baby and you can't read. Or maybe it's covered in dirt and you can't read it. So there'd be a lot of counterexamples. I'd go ahead and call that one false. Let's look at B. Switching it up a little bit again. This time we're leaving it kind of in that if-then order, but we're just putting in some nots. So if you cannot read this, then you're not too close. So a scenario, what you're looking for here is a scenario where you can't read it, and it's saying that you're not too close. So maybe I am too close. I can't read it. Maybe I am too close. Can you come up with a counterexample? And I'm not going to go through all these we did in class, but that's kind of the scenarios. You just have to look at this, and you have to take the if part. The if is what's given, and you know that that's true. The then is what you're trying to find a counterexample on. All right, so let's look at some. Okay, the if part I said is the given. I like to use that word given. It's also the hypothesis. That's what we're assuming to be true. The conclusion is the then part. It's what we're trying to prove. This is the notation we use right here. It's read if P, then Q. And it's just like P represents your hypothesis part of your statement. The Q represents your conclusion part. What are the hypothesis and the conclusion of this conditional? If an angle measures 130, then the angle is obtuse. The hypothesis is the if part. So I'm going to write the hypothesis would be, I have this angle, and it measures 130. That's the if, the given, the hypothesis. An angle measures 130 degrees. Okay, got it. The conclusion is your then. Okay, so my conclusion is the angle is obtuse. It says, do you think this conditional is true, or can you come up with a counterexample? Okay, so do you think if an angle measures 130 degrees, so envision you've got this angle, it's 130. They're saying that the angle is obtuse. Is there any way that you could find a counterexample? In other words, find a 130 degree angle somewhere that does not end up being obtuse. I don't think I can do it. I think this one's true. I cannot come up with a counterexample on that one. So I think their conditional there was true. How can you write dolphins are mammals as a conditional? Okay, so this one doesn't have it's not written as an if-then statement. So when they say to write it as a conditional, you put the if and the then in there to kind of separate it. So first thing you got to do is identify the hypothesis. The hypothesis is that I have a dolphin here. The conclusion is I'm saying that it's a mammal. Then we're going to write it with an if-then. So if the animal is a dolphin, then it is a mammal. And then sometimes it's easier if it's in this if-then form, it's easier to do your counterexample and that kind of thing. Because you know that to come up with your counterexample, this part has to stay true. This always is true. You're trying to find up a way that this would not end up being true if this was. I think this one's true. Your classmate rewrote the statement, you jog every Sunday, as the following conditional. Now, before I even read it, I think, you jog every Sunday. Think what that means in your head, if you jog every Sunday. And you're trying to turn that into an if-then. If you jog, then it's Sunday. That's not right. When you say you jog every Sunday, you jog on Sundays. If it's Sunday, then you're jogging. But not if you... This isn't saying I only jog on Sundays. And that's what my classmate conditional says here. If you jog, then it's Sunday. That's not what this means. If I'm jogging every Sunday, I would rather it say, if it is Sunday, then you jog. it does not always go in the same order as it's read. So you have to understand what the intention of the statement is before you turn it into a conditional. When testing a conditional, the hypothesis is always assumed to be true. This is important. The first part, the hypothesis part, the if, that's assumed to be true. When you're coming up and you're trying to decide if it's true or false, you're trying to find a counterexample that keeps the hypothesis true but makes the conclusion end up being false. So let's keep practicing. If a number is divisible by 3, then it's odd. We're deciding true or false. So to say it's false, we have to find a scenario where this holds true. I got a number, it's going to be divisible by 3. But I want this to end up not being true. So if it says then it's odd, so I'm really trying to find something that's even. A number that's divisible by 3, but ends up being even. Do you got it in your head? I'm going to say this one's false. And my counterexample would be 6. Now there's multiple counterexamples. Maybe you thought 12. I don't know. There'd be a lot of them. That's my counterexample. All right, so these are for you. I want you to kind of practice this conditional, the if-then, deciding the true or false. If you say false, you have to have a counterexample for it. All right, so I want you to pause the video here and do 3A and B. All right, I marked them both as true. I think B, I'm going to start with B actually. If two angles form a linear pair, then they are supplementary. We actually have a postulate from chapter 1 that stated that. I drew my picture. Here's my linear pair. I've got this angle here, right here, and this one here. These angles, if they form a linear pair, they will always form this straight line, which is going to force them to be supplementary. So if I'm going to try to say I have a linear pair, yep, they're going to be supplementary. I'm not going to be able to do a counterexample on that. This first one is a little bit tricky, just depends on how you interpret it. I wish they had said, instead of if a month has 28 days, I wish they said if a month has exactly 28 days, then it's February. Because all of the months have 28 days, but then they might have a few more also. They might have 30 or 31. But I'm going to assume it meant that if a month has exactly 28 days, then it's February. For me to find a counterexample, I would have to find a month that has 28 days, but it could not be February, and that's not the case. February is the only one with 28 days. Okay, let's look at one other thing here. The negation of a statement is the opposite of it. So instead of saying something does have something, it does have 28 days, or it does form a linear pair, we might say that if a month does not have 28 days, and we put this not in there. If we put a not in there for our symbolism, and we use this symbolism for kind of a shortcut, the whole if P, then Q idea. Now, if you put in a little squiggly line in front of it, that means if not P. So if P's not true, then Q. Or I might put it in front of the Q. It's just a squiggly line, means not. Now, we're focusing mostly on conditionals, but all these conditionals can be reworded kind of like the bumper sticker was, and that's really what that was doing, was giving you all these other ways to rearrange it. This is my standard right here, if P then Q, that's the standard. If I switch it around, if I switch the order, that's called the converse. So my if and my then statements are flip-flopping. Sometimes that's still going to be true, sometimes that's not. It just depends on the statement. The inverse of a statement goes back to the original order. You can see that it's still the P and then the Q, but we're going to put nots in front of both of them. The contrapositive messes it up as much as it can. It's going to flip-flop the if and then, and it's going to put nots on it. Okay, let's look at some of these. We have a conditional. It says, if the measure of angle A equals 15, then angle A is acute. That's the conditional. I tried to make it short here because we're going to write all of these. This is your if, this is your hypothesis, and then this is the then, angle A is acute, that's the conclusion. For the converse, and you're going to have to peek back at that previous slide to remember on what each one of these does. The converse actually switches the if and then. If you look back, it says if Q, then P. Switches the order. So I'm going to write that. If, and I'm going to switch it around, angle A is acute, then the measure of angle A equals 15. Right now we're just going to practice writing these, and we'll come back and talk about them. All right, let's talk about the inverse. The inverse, if you look back at the previous slide, kept the same order. It was PQ, but it put knots on it. So it's if not P, then not Q. So let's rewrite this. In the same order, so it's if the measure of angle A, and I'm going to say does not equal 15, then, and I follow up with the conclusion, angle A is not acute. All right, last one. Contrapositive messes it up totally. It's going to switch the order and put knots on it. So it looks if not Q, then not P. I have to switch the order and put knots. So it's going to be if angle A is not acute, then the measure of angle A is not 15. You need to kind of get familiar with those different terms, the converse, inverse, contrapositive, and how that adjusts your conditional. Once we have them, we're going to look and say, okay, well, does that change whether it's true or false? So I'm going to go back on each one of them and decide if they are true or false. On the very first one, the original conditional, if angle A is 15, then angle A is acute. That's a true statement. Yes, that's true. Let's look at the next one. If angle A is acute, then the measure of angle A is 15. Remember, if I want to say false, I have to make this hold, but find a counterexample for this. So I have to find an angle A that is acute, but that it's not 15. I can do that. I would just pick a different value for angle A. So I would say false, and my counterexample is that measure of angle A equals 20. And we, of course, could all have different counterexamples there. All right, next one, the inverse. If the measure of angle A is not 15, so you got to think about it. Angle A can be anything else. It's not 15, though. Then angle A is not acute. All right, for me to say that this is false, I have to keep this true. So I'm thinking of a measure for angle A that's not 15. And then I need to show that this is not accurate. And I would basically be doing the opposite, so I'm going to take out this not. So I need to find an angle A, have some value, measurement, then angle A is acute. Okay, I think I'm back to this same counterexample. If the measure of angle A is not 15, okay, I'm going to make it be 20. Measure of angle A is 20. Then A is not acute. Well, yes, it is acute. All right, so I'm going to go false again, same counterexample. Last one. If angle A is not acute, so I have to think in my mind that has to hold true, so angle A is obtuse, probably, could be right, but I'm thinking in my head angle A is this big angle, this obtuse angle. Then the measure of angle A does not equal 15. Well, I'm envisioning this big angle, right? Angle A is not acute. It's got to be like obtuse. Then the measure of angle A is not 15. Well, that's true. It's not. It's a lot bigger than 15. So I think this one would hold true. Okay, it's kind of tricky. It gets kind of wordy. You got to be careful with some of these. All right, this is the last one, and I want you to try this one on your own. Go through and figure out. You're doing the same thing we just did. Practice writing what each one of these is, get familiar with what you do in each scenario, then come back and decide if each one is true or false. Pause the video, and go write this on your own. Come back when you're done. All right, here are my statements after I converted them all. The figure is a square, that's the p-value. Then it's a quadrilateral, that's the q. So the converse just switches those around. If the figure is a quadrilateral, so think in your head, okay, got a figure, it's a quadrilateral, it's got 4 sides. Then it is a square. All I got to do is find one example of something that's 4-sided that's not a square. How about a trapezoid? I'm going to go false. And I'm going to write trapezoid. And we actually do a whole chapter on quadrilaterals, but if you've forgotten what a trapezoid looks like, it's this right here. And it is not a square. Okay, let's look at the next one. If a figure is not a square, so in my head, I got this figure, it's not a square. I'm going to think for a second that it's a rectangle, I don't know. Okay, then it is not a quadrilateral. Well, hang on. It is a quadrilateral. I said rectangle, right? I've got this rectangle in my mind because that's not a square. So the first part holds true, but the second part is not. It's not a quadrilateral. Yes, it is a quadrilateral. It's a rectangle. So I'm going to say false, and I'm going to say rectangle. I could have also said trapezoid. That would have been a good counterexample. I forgot. I should have begun with the very first one. I didn't do the given conditional. If the figure is a square, then it's a quadrilateral. I'm going to say that's true. All right, last one. If the figure is not a quadrilateral, so you do not have a 4-sided figure, then it is not a square. I think that's going to hold true, because if it can't have 4 sides, then I can't make it be a square. So I think that's going to hold. That's a true statement. All right. A lot of these will be multiple choice from Math Excel, so hopefully you don't have a monster amount of writing for your homework. All right. Good luck. Hope this helps.